In this video, we are going to go through how to program the water supply calculation template. So again, I created a template for you guys to use, and it is also color coordinated. So we'll begin with that. Anytime you see a yellow cell, that is going to be a user input value. It can be either a word or a number, but there are no calculations. And then when you go from example to example, you'll delete the values in here because it'll change example to example, but you won't be changing any of the green or the red. The green and the red are going to be your calculation cells. It's going to be equal to this cell, some kind of mathematical operation, then another cell. Red are your intermediate values. Green are typically your final answers. So we'll get started. So when you get a water example, you'll be told a starting elevation and an ending elevation typically. Starting elevation is going to be your water tower. Ending elevation will be your home's elevation. So because they're yellow, you're going to be inputting the value. And then the first answer you're going to get is going to be the static head, which is the elevation difference between the water tower and your home. So I'm going to say this is equal to this cell minus this cell. And that gives me my static head in feet. Once I have my static head, I'm going to want to know what my static pressure is. And if you remember from the PowerPoint, 1 psi is equal to 2.31 feet. So if I want to go from feet to psi, I'm going to say that this cell is equal to static head divided by 2.31. Easy enough. So let's come over here to our fitting type. So you'll be told your water supply pipe goes through 15 regular 90-degree elbows and 22 line flow tees, whatever. So you're going to type in what it is over here, whether it be regular 90-degree elbow. And this is really just there to kind of help guide you. It's not necessarily going to be used in your final calculation. Here is where it does matter. You'll be typing in the quantity here, and then the equivalent length right here, using the chart. I think I have it up. Right over, yeah, here we go. Using this chart over here. So I'm going to have this cell right here be equal to the quantity multiplied by the equivalent length to give me the total equivalent length for each of the individual fittings. And similar to the heat transfer one, I'm then going to copy down the logic because I don't want to type it in for each individual one. You can type it in for the first one. I don't want to do that. That takes too long. I'm going to type it in one time, and then I'm going to copy the logic down for the rest of them. So look at my cursor. Fat white cross, nope. XY direction, nope. Go to the bottom right corner where it turns into a thin black cross. Boom. Click, drag, hold, go down. Now each of these cells is going to just be the G times the H for that respective row. Look over here as I change. So, like we often do, we multiply across and add going down. So this is going to be equal to the sum of the above cells. So what we just calculated now is this is the equivalent length of all the fittings. Next, we're going to come down here. And over here, it might look a little tricky, but it's not that bad. So basically, different problems will be worded in different ways. Sometimes I'll just tell you, hey, the overall system is 3 miles. Sometimes you'll see it as like a map where like the first line segment is 200 feet, then the next one's 500 feet, then the next one's 0.3 miles, and it varies. So we want to create a program that will be able to handle several different pipe segments and can also handle it being expressed in miles or feet. We want to be able to handle either one. So the way we have it this way is if it's miles, you type in the miles. If it's feet, type in the feet. And on the bottom, we're going to ultimately give our final answer in feet. That way, no matter what it is, miles or feet, your final answer will be converted to feet. Because that's how the ultimate Hazen-Williams formula wants it. So I'm going to say in this cell right here, I want this to give me the overall miles that we've traveled. So sum of the above cells. H24, I want this to be equal to the sum of all the respective feet segments. Then my total linear length is going to be equal to, well, again, I'm trying to make the final answer in feet only. So if I have miles and feet and I want it into feet, I'm going to say that G25 is equal to G24, which is a total number of miles, multiplied by 5,280, and that'll convert the miles to feet. And then now that it's feet, I can just add the other feet. So let's test it out. If I have 1 mile, I go 5,280 feet. If my next section is 200 feet, this should go up by 200 when I hit enter, and it does, so it works. Let's go over now to here. So when I have my examples, typically Q will be given to you. We'll just type in a random value. It's typically between 90 and 110. The C is the Hazen-Williams constant based on the material, that little chart over here. We'll just use 100 just to have a placeholder. D will be given. It'll be just the thickness or diameter of the pipe. Maybe, 8 inches is typical. And then length. This is the total equivalent length. Different than the total equivalent length of fittings, but that's only the fittings. Our total equivalent length is the linear length plus the equivalent length of fittings. So C12 is going to be equal to this plus this value right here. Our head loss, well, that's going to be our lovely formula. So I'm going to do that in a second, but let's quickly just do dynamic head and dynamic pressure. Head loss will take a little bit longer, so we're going to just skip it just temporarily. Stick with me. Now, let's just assume for a second we had the head loss. If we know our head loss and we already know our static head and our static pressure, we can easily find our dynamic head and dynamic pressure. So I'm going to say my dynamic head is equal to my static head measured in feet minus my head loss measured in feet. And once I know my dynamic head, dynamic pressure is very easy. My dynamic pressure is equal to my dynamic head divided by 2.31. So let's go back to head loss. Let me see if I can quickly pull up the formula for it. There we go. So we have h of f is equal to 10.44 times L times 2 to the 1.85 divided by C to the 1.85 times D to the 4.8655. Ugh. Well, that's kind of a weird formula. This would be a very unpleasant formula to do using a calculator, especially multiple times. But let's type it into here. So when I type it into here, the most common mistake that I do, or that I see, is people not properly using parentheses. So we have 10.44. This is the wrong way to do it. Let me say that again. Right now I'm doing it the way that people often make a mistake. 10.44 times L, which is this cell right here, times Q. And when we do exponents, you're going to do a little caret, control 6, to the 1.85 divided by C to the 1.85 times D to the 4.8655. Again, this is the wrong way to do it, but I see it all the time. Why is it wrong? Because this is doing PEMDAS, so it's going straight across. So when it's doing 10.44 times L times Q, that quantity divided by C, and then that quantity multiplied by d. What I really want is to have the numerator and the denominator separated. So I'm going to do parentheses around the entire numerator and then parentheses around the entire denominator. There we go. So let me just throw in a quick value right here. These are just kind of random numbers to make up. And throw in a and there we go. So here is our finished Excel program for water supply template. In the next video, I'm going to do a little bit more advanced programming to kind of help give you some logic. Some people, myself included, we don't like seeing, so I'm going to delete everything. We don't like seeing all these zeros here, nor do we like seeing these error messages. So I'm going to show you how to add logic to eliminate this so that it's going to be a blank cell until the very end when it gives you your correct final answer. All right, later.